homology of diagram, in fact, the link, as we will see below, D. And as was already explained, it is a finer invariant than Jones polynomial. For example, Khovanov homology is able to detect the unknot, while Jones polynomial is not known if it can detect the unknot or not. I'm sorry for this point. Okay. Now I want to just muse a bit more about this construction. So let me draw...
Прошу прощения, а можно еще один технический вопрос задать?
Yes.
Когда берется тензорное произведение вот этих двухчленных комплексов, дифференциал D нечетный, соответственно, там, когда перескакивает, знак меняется, когда мы определяем в тензорном произведении дифференциал. Тогда все зависит от того, в каком порядке их тензорно умножать. Вот в каком порядке нужно тензорно перемножать эти двухчленные комплексы, соответствующие различным двойным точкам. Это от этого упорядочения, его нужно как-то фиксировать или от него вообще никак не зависит? Как? Ну вот у нас каждому пересечению соответствует такой двухчленный комплекс, правильно? А мы берем их тензорные произведения по всем пересечениям? Или как?
Нет.
А как мы берем?
Сейчас объясню. Сейчас объясню, как мы берем. Okay, so yes, so let me just. Sorry, I seem to be missing something here. No, it's okay. Let me just explain a bit more. I will explain the construction more rigorously later, so I hope that I'll answer.
Но пока у нас дано определение одночленного комплекса, которое обозначается пустое множество в квадратных скобках, есть определение двухчленного комплекса, которое обозначается одно перекрестие в квадратных скобках, а дальше из этого каким-то образом изготавливается комплекс D в квадратных скобках, который нигде пока не записан. Нигде не определен пока, правильно?
Yes. Yes, that's true. Okay, so I wanted just to give some visualization of this process. So since we have this set right here, immediately brings to mind various sorts of cubes, and that's precisely how it should look. So we can draw a cube which corresponds to all possible resolutions of our diagram. Its vertices are encoded by sequences of ones and zeros. We have a cube. Vertices correspond to resolutions, and each vertex carries either q plus q inverse if we are raised to the power of number of circles corresponding to this vertex. So each vertex iota carries this number of factors of q plus q inverse, or it carries a tensor product taken ki times if we're talking about Khovanov homology.
Recording in progress.
So now, when we're computing Kaufman bracket, we just need to take the following sum with signs. So we take the sum over all vertices of a Q with the following sign and multiply it by these factors.
Grisha, once again, you mean D in the bracket inside the
bracket? Yes. Thank you for correcting me. Yes. So that's the way to compute Kaufman bracket. And for a trefoil knot, after normalizing this term, we obtain. This formula is very clear actually because this term right here comes from the number of times that we apply that we get the one resolution in our total resolution. So this modulus of I is just a sum of coordinates of I. And so this term right here is very clear because we just count the number of one resolutions here. So recall that we multiplied by minus Q each time we applied this one resolution. And so this term appears right here. And this is just the value on disjoint union of circles. So this formula is very clear. And the value of unnormalized Jones polynomial on a trefoil is the following thing. So that corresponds to a trefoil. Hopefully I'll be able to draw it here. Yep, that is it. So that's a diagram of a trefoil, which is standard one. Okay, and so to compute Khovanov bracket, we do the very similar thing. We just take a direct sum of complexes of the form k alpha b to the tangent power k alpha over all alpha in to the power of I, and then we just sprinkle some differentials on it and some shifts. So actually, I think we should shift it here by like order I or something like that, but I will explain it later. So I'm just introducing the setting. And now I can do everything rigorously from now on. So first of all, I will. So now. First of all, I need to introduce Q dimension. As was said above, it's just a sum of QR to the power. So it's a sum of Q to the power R and multiplied by dimension of the corresponding component. Okay, so that's the Q dimension. Another thing is, of course,
so that our vector space W is just the direct sum of WR.
Yes, so it's Z-graded vector space, which equals yeah. So the second one is sort of vertical shift. Let's call it like that. So we can shift a graded vector space by L, and by definition, we have here Wm minus L. And so the Q dimension of this shifted vector space is just a multiple of the initial Q dimension. Here it is important to remember that Q dimension is just a notation, and the letter Q does not play any full row here. So it's not like a multiple. Okay, so that's a vertical shift and a horizontal shift of a chain complex. So let's have a C, which is a chain complex on vector spaces. And the horizontal shift looks like this. So we have cohomological gradient here. And differential is transformed like this. Sorry, I need to write here. The shift of differential. Okay. So I think those were algebraic preliminaries you need for this theory. It is not very complex, in fact. So now I will give a rigorous definition. So once again, I is, okay, so I need to stress what I'm doing here. Definition of one of bracket. So once again, I is a set of intersections.
Is it indeed a bracket or just homology?
Yes, I mean.
Okay.
What is your definition of a bracket? Let's say this.
Okay, let it be a bracket.
Yeah, I mean it's the name that was given to it by Barnatan, and it is even in Wikipedia. So I think now it's somewhat standard to call it a Khovanov bracket. Okay, so N is cardinality of the set of intersections, and N plus or minus is as above, so those are positive or negative intersections. Okay, and so V is actually more than just a vector space of graded dimension Q plus Q inverse. It is in fact a vector space which is generated by two specific variables, V plus of degree 1 and V minus of degree minus 1. And so what we do here is we just, I'm sorry, why I wrote R here. So V iota is just a tensor product of K iota, that is the number of circles in resolution iota, of K iota copies of V, shifted by the height of iota. So the height of iota as above, just a sum of coordinates of iota. Now, the Khovanov bracket is in degree R, is the following complex. Not a complex, I'm sorry, graded vector space. So we take all iota with height R, and we take the sum over all such iotas of V iota D. And so the complex or Khovanov bracket, for that matter, is just the Khovanov bracket is just the sum of all its components. And this normalized Khovanov bracket is the following shifted complex. So this complex should be, so this is the complex that computes Chom's polynomial as its Euler characteristic.
Да, я прокомментирую. Значит, само название гомология Khovanov. Наличие гомологии предполагает, что у нас есть некоторый комплекс. Комплекс – это набор или последовательность векторных пространств.
I will construct the differential later, if you want to.
Значит, у нас должна быть последовательность векторных пространств и последовательность их отображений, дифференциалов между этими векторными пространствами, обладающая тем свойством, что композиция двух последовательных дифференциалов является нулем. Тогда мы можем говорить о том, что у нас есть комплекс и вычислять его гомологию. Значит, в качестве пространств здесь берутся следующие пространства. У нас есть некоторое основное двумерное пространство V, в котором еще к тому же выбран базис со степенью одного из векторов равно единице, а второго базисного вектора равно минус единице. И дальше для каждого разрешения нашей диаграммы, значит, у нас есть диаграмма с n двойными точками. Каждую точку мы можем разрешить одним из двух способов. Либо способом 0, либо способом 1. По Калдену, скажем. Вот. И для каждого мы фиксируем набор йота этих разрешений. Вот. И для такого фиксированного набора разрешений мы строим векторное пространство, которое является произведением тензорной степенью нашего исходного пространства V в количестве равном количеству окружностей, которое получилось при этом разрешении. Значит, когда мы зафиксировали разрешение, у нас проекция узла распалась на некоторый конечный набор окружностей. Вот количество k йота этих окружностей в этом разрешении мы и берем в качестве тензорной степени пространства. Вот. И, значит, наш... Вот тут написано скобка R-тая часть скобки. Это прямая сумма всех таких векторных пространств, относящихся к разрешению, в которых было ровно R единиц. Значит, n минус R нулей и R единиц. У нас получается такое большое пространство, прямая сумма всех пространств по всем наборам окружностей. Вот. Ну и само пространство – это прямая сумма по всем R. Всех таких пространств D, но там еще нужно немножко подправить градуировку, чтобы получившееся пространство совпадало с той градуировкой, которая стоит в определении многочлена Джонса. А сейчас будет определен, как я понимаю, дифференциал. То есть как мы устраиваем дифференцирование в этом пространстве. У нас есть последовательность пространств векторных, но нам нужна еще последовательность их отображений, то есть последовательность дифференциалов. Вот сейчас Гриша переходит к определению дифференциала, если я правильно понимаю.
Прошу прощения. А как подправляется градуировка? Что такое минус n, минус и...
So that's the shift in the complex direction. So you can shift the complex or... So basically, you have two gradients on this space, right? Here. So you have a gradient by R and a gradient inside of each of those guys, right? So you can shift by, so the curly brackets mean the shift by vector space direction, graded vector space direction. And square brackets means the shift by direction of this complex for now just by R direction.
Okay, got it. Thanks.
Okay.
Да, я еще извиняюсь. Я правильно понимаю, что вот там, где мы определяем D в скобках RT, йота должна лежать в кубе, а не в I?
Yes, thank you.
Спасибо.
Yes, that's very valid point here. Okay. So now I can define a differential indeed, but first I need to talk a bit about edges of this tube. of edges of this cube. So edges of this cube are encoded by the following sequences. So we can take the 3-element set, and here each edge corresponds to a sequence where there is exactly one star. So the sequence of length m with exactly one star. How so? Well, we just to find the tail and the head of this edge, we just need to evaluate this star at 0, so that's the tail, or evaluate this star at 1, so that's the head of our edge. And now, what we have here, we have a grading on edges, so that's just, by definition, that's just grading on edges. So that's just the gradient of the tail of this edge. And so we can define the differential. Wait, I'm sorry. I tried to sneak into the bracket. And it is defined like this. So we just take the sign here, and we take the sum over all edges which start at this at vertices of height r. So that's the definition of the differential modulo the fact that I didn't define d sigma, c yet. But I will do it in just a moment. So first I need to explain where the signs come from. Well, the signs come from the fact that we really need the differential to be differential. So signs for this equality here. So now what we need to do is to understand what is happening at each edge. So the very convenient thing to do here is to think about it like one-dimensional cobordism. So at each edge...
Значит, еще разок. Дифференциал определяется следующим образом. Мы берем и заменяем в данном разрешении нашей диаграммы одно место, где было разрешение нулик, мы заменяем разрешением единичка.
I was just about to talk about it.
Yeah. Sorry.
Yes. I was just starting to explain precisely this point. So it is convenient to think of it like this. So we had a resolution here at the tail of the edge, and perhaps we had two circles here. It became one circle, and all other circles did not do anything on this edge. So they're just idling here around this surface. So that corresponds to mapping from tensor product to V. And it is natural to think of it as a multiplication in a certain algebra. Well, in fact, it is a Frobenius algebra. Anyone, if someone is familiar with one-dimensional TQFTs, one should know that one-dimensional TQFTs correspond to Frobenius algebras. But I will give this multiplication explicitly. We can turn this V into an algebra, in fact, into a bialgebra, by defining this multiplication like this, or just on generators. So, I'm sorry. My pen is misbehaving. Yeah, so it maps to 0, and we define the multiplication, and now we need to define the comultiplication. Comultiplication, of course, corresponds to the moment when one circle becomes two circles. And of course, this idling here corresponds just to identity. So we really should think of the cobordism like encoding some algebraic operations here. So this cobordism encodes multiplication, this cobordism encodes comultiplication. So comultiplication works like this. Okay, so I should warn that it is not.
Grisha, indicate
Yes.
please that delta maps V to V tensor V.
Yes, yes. So we have an exemplar of V here, exemplar V here, and V here. So yes, we map from V to tensor square of V. Yes, thank you. So basically now I can define what is this differential. So the differential is just the sigma is just delta or m for the corresponding address. So if a circle,
Sorry, it's psi rather than sigma. D, what is the index of D?
It's like this. I think it's
psi. Yes.
psi. Okay. Yes. Thank you. So it's psi. Yes. So d psi is just multiplication or multiplication. There's a multiplication when two circles merge into one, and it is a co-multiplication if two circles are born from one circle. Okay. So now we're actually all good to go because we define a certain complex with a differential, which is skew commutative on edges, on square faces of a cube. Thus, we have this formula. It is indeed a differential. And so we've defined a certain complex for each diagram.
It's not a complex yet because you have not proved that this is indeed a differential. But this is what can be left as an exercise. Значит,
yeah, I think.
Домашнее задание всем – это доказать, что то, что получилось, это действительно комплекс векторных пространств, то есть, что d в квадрате – это 0. Если мы берем композицию дифференцирования, композицию операторов d, то это действительно будет всегда нулем для любого элемента.
Простите, а факт, что если мы проходим вдоль одного ребра вашего куба, то число окружностей меняется ровно на единицу, это очевидно.
Yeah, it's by definition because R was precisely the number of circles.
Точно, да.
Yeah, so that's by design. I actually.
Sorry, R was the number of positive of ones. It's not the number of.
Sorry. Yes.
Yeah. Nevertheless, this is indeed obvious because under replacing 0 with 1, we can either split a single circle into two or glue together two circles into a single one.
But why positive direction correspond to splitting the circles?
Не понял. Значит, когда мы меняем нулик на единичку в каком-то месте, у нас там встречаются две дуги окружности. При этом либо они принадлежат одной окружности, и тогда эта окружность расщепляется на две другие, и тогда мы должны использовать оператор дельта. Либо они принадлежат разным окружностям, и тогда эти две окружности склеиваются вместе, получается одна окружность, и мы должны использовать оператор m, умножение.
Это, да, понял, либо то, либо да.
Либо то, либо другое, либо дельта, либо m. Но отличие всякий раз ровно на единичку.
Да.
Okay, so yeah, so we stated this exercise, and so without the signs, the cube is commutative. So it is not very hard to prove. It follows from functoriality of this assignment. And then it is straightforward to prove that it is indeed a quantity. Okay. So now I am ready to state the main theorem, which was in my abstract. So P char of D is the Earth's homology. Or cohomology, it doesn't matter here because we don't have any multiplication and the difference is just notational. And so this Khovanov polynomial is now a polynomial in two variables instead of one. It's just a graded Poincare polynomial. Defined like this. Okay. So now I think I'm, yeah, and
what is the statement of the theory?
Yeah, so is well, but still is a link invariant. And one of polynomial specifies to Jones polynomial at t equal -1. So after proving that it is in fact a link invariant, it is straightforward to verify this equality. Because we just constructed a complex with differential degrees. So yeah, short note on the last statement. So it is straightforward to verify this fact because D in C of D is of degree 0 in vector space direction. So that's another reason why we need to shift vector spaces in the definition of this complex. And so
probably it's best to return back to the definition of M and delta so that one would be able to see that.
Yeah, so degree of m and delta is -1.
Значит, когда мы отправляем v плюс тензор на v плюс в v плюс, мы понижаем суммарную степень на единичку. То есть и для остальных, в остальных случаях также. То же самое для дельта, для операции дельта. Поэтому операция m и дельта понижает степень пространства на единичку, но когда мы делаем сдвиг градуировки, то они оказываются в степени 0.
Yeah. And so so now we have a zero differential of degree 0, and we have a complex of finite dimensional vector spaces. So its Euler characteristic, coincides with that of H star. And so then it is absolutely straightforward to see that at each vertex we have precisely the term which corresponds to Kaufman bracket, to the computation of Kaufman bracket. And well, this last statement is really trivial by design. So,
то есть на самом деле комплекс Хованова распадается в прямую сумму комплексов, каждый из которых имеет одну фиксированную степень. У нас дифференциал – это отображение нулевой степени. У нас поэтому комплекс такой просто набор комплексов одной степени. И Эйлерова характеристика комплекса там степени k – это в точности коэффициент при q в степени k в многочлене Джонса.
Yes. So the really hard part here is to prove that this C of D is independent up to quasi-isomorphism from the specific link diagram. So it's invariance under Reidemeister's moves. So now to the proof of the main theorem. So let's once again look at this theorem. We need to prove that it is a link invariant, and we will do this by proving that it is an invariant under Reidemeister's moves. So first of all, I'll have to recall what are Reidemeister's moves, although perhaps it is unnecessary here, but nevertheless, it's better to recall. So that's R1, R2 looks like this. And R3 looks like this. Okay. So we once again are guided by the way we prove something similar about Kaufman bracket. Well, Kaufman bracket is itself not invariant, but Jones polynomial is because of renormalization. So for the Kaufman bracket, we have something like this. So by applying the axioms of the bracket, we get the form. And so we basically proved an invariance under Reidemeister's move number 1. because here is this multiple, but it's precisely what it should have. Because after normalization, we just kill it off. And now, to prove the same...
Да, значит, мы разменяли одну точку самопересечения диаграммы на коэффициент q в минус 1, а это в точности означает, что мы сдвинулись на единичку, сдвинули градуировку на единичку.
Сейчас еще раз. Как мы получили q плюс q минус 1 и перерисовали?
Well, that's by the axiom, because we have a disjoint union of a circle and this thing here. And we had an axiom that Kaufman bracket behaves like this.
Определение скобки Кауфмана предполагает, что мы можем удалить отдельно стоящую окружность за счет умножения на q плюс q минус 1.
Okay, so that was a motivating example. And to do similar things with chain complexes, we'll have to devise a lemma about cancellation of chain complexes. Well, it is actually quite simple, a trivial homological lemma. So if we have a chain complex, and then there is a chain subcomplex, then we have the following relation. If C prime is a cyclic, then homology of C modulo C prime is the same, I don't know, by this quasi-isomorphism, meaning the same homology, is the same as homology of the initial complex. Similarly, if C mod C prime is a cyclic, then we have a quasi-isomorphism between C prime and C. So that's
Значит, это обозначение не очень хорошее для квазиизоморфизма, потому что Q у нас используется в другом смысле и является... Просто напишите, что имеет те же гомологии. Два комплекса имеют изоморфные гомологии. Ну, можно так.
Okay, so that just immediately follows from the long exact sequence in homology. Okay, and now the proof of R1 invariance. So to compute Khovanov homology of this intersection, we need to consider a complex of the following form. Okay. So we have a subcomplex C prime and C, which consists of the following. So we take total complex of the following double complex. I will explain this V plus in a moment.
Я неправильно понимаю, что отображение M должно отправляться в склеенную кривую, а не в ту же самую.
Сейчас, кто должен отправляться?
Вот здесь, вот там, где у вас стоит стрелочка, кривая должна быть склеенная.
Где стоит стрелочка? Да, сейчас что-то я, да, не могу. Yes, thank you. So I have to explain what's happening here. You see that this guy right here is a vector space spanned by cycles. So this is a vector space spanned by linear combinations of cycles. So cycles. And we have a distinguished cycle right here. So in each resolution, we have this particular cycle in each resolution of this diagram. And this cycle should correspond to V plus in a subspace, which we denote by these square brackets, sub V plus. So once again, this Khovanov bracket is a vector space which is spanned by marked cycles. So to each cycle, we give a marking either V plus or V minus. So we can have both, of course. And this subspace consists of those linear combinations where this particular cycle is marked by V plus. That's what is happening here. Is it clear? I can reiterate my point. So
I believe yes. Yeah. Mm-hmm.
Okay. So now C prime is a cyclic since V plus is a unit of M. And so, yeah, so this is an acyclic subcomplex, and thus homology of C is the same as the homology of the quotient. And the homology of the quotient is just homology of the Coulomb complex. Oh, sorry. Sorry once again. Yeah, so and here we should mod out by V plus. So we say that V plus should be equal to 0. Okay. So this thing right here, I think, completes the proof of the fact that homology of this thing is invariant under Reidemeister's moves.
Гриш, ну так доказательство инвариантности относительно двух оставшихся движений, оно похоже на доказательство инвариантности. Здесь, может быть, лучше показать пример вычисления.
Okay, yes, I can do that. Certainly. Yes, so you're absolutely right. The proof of the rest is similar. We just find an acyclic subcomplexes or quotient complexes and we mod out by them. Yes, okay, so we've proven R1, the rest is similar. So now I think, yes, I can give an example of computation. So unfortunately, I don't think that it will be a very interesting one, but I can compute an example for trefoil knot. So we start by drawing this cube, which was already mentioned. So this corresponds to the following sequence of integers, and here we should have v, just v, because we have only one circle, and it should be shifted by, yes.
Why there is 1 and 2 zeros?
Because we have like this set.
But
No.
Shouldn't it be start with 3 zeros, or this is not?
No, 3 zeros look different.
I see. Right.
3 zeros are just, I'm drawing them right now. 3 zeros have actually 2 circles instead of 1. So that's 3 zeros. Here, the space is unshifted because the sum of coordinates is 0. And so that's the 0, sorry, I'll have to draw a lot of trefoils here. So that's the 0 component. Here we have the 1 component. So we should sum them up like this. So here we of course have once again v shifted by 1. Here v shifted by 1 as well. And so that's the component degree 1.
Значит, у трилистника в стандартной диаграмме трилистника 3 точки самопересечения, поэтому каждая из 3 точек можно разрешить либо способом 0, либо способом 1. Мы получаем 8 возможных разрешений. И вот эти 8 возможных разрешений Гриша сейчас изображает. И каждому разрешению соответствует тензорная степень векторного пространства V. В количестве показателя степени равен количеству окружностей, которые получаются при этом разрешении. Ну и, соответственно, имеется отображение между этими пространствами, которое соответствует умножениям или разумножениям в зависимости от того, у нас 2 окружности заменяются одной или 1 окружность 2. Вот этот куб в таком разрезе, что сначала слева там начальная вершина куба, потом 3 вершины, соединенные с ней ребрами, потом 3 вершины, соединенные с этими 3, и потом справа будет конечная вершина куба. Там еще внизу одно отображение.
Yes. So 3 different circles here.
Можно вопрос? А в конечном итоге мы должны получить столько кругов, сколько у нас точек пересечения было?
Нет, это совершенно не обязательно.
Значит, как получится?
Как получится, так и получится.
Наверное, для торических узлов это правда. Я как бы не великий специалист.
Количество окружностей, ну, я совершенно не уверен в том, что всегда можно построить разрешение, которое дает столько окружностей, сколько было точек пересечения в диаграмме. Это, по-моему, ниоткуда не следует.
Okay.
Сейчас там разные способы разрешения дают разное число окружностей.
По-разному. Okay, so what we get here after normalizing our Khovanov bracket, so that's we can I think in the we get this complex and its graded Euler characteristic is equal to what it should be equal. That is the Jones polynomial. I think not exactly this. It's not Q plus. It should be also multiplied by this thing right here. So that's the Euler characteristic of our context here. I don't know. Maybe it's not the best example of computation, but that's the one I have. I mean, here you can at least see how we construct this tube and this complex from which we compute Khovanov homology.
Ну, напишите этот комплекс, оставив только векторное пространство. То есть V-тензорный квадрат в прямую сумму V сдвинутых на единичку, трех копий V. Хорошо? Гриш, слышите меня?
Да, сейчас да.
Да, напишите, пожалуйста, этот комплекс, вот, оставив только векторное пространство ниже. V-тензорный квадрат, куда отображается. Нет, в этот самый... Линейно, да. Ага. 3 копии. Угу. Угу. Лучше писать v плюс v плюс v, потому что иначе непонятно, что такое v в кубе. Угу. Вот так вот, да. Угу.
Because the tail of each edge it's the same vertex and it has degree 0, as can be seen here. Mm-hmm. So that's the map here. Then we have 3 tensor squares. And it's mapped by, I have to, I mean, everything here is symmetric, so I think I can just define it on one vector space, and then everything can be extended to others. So, so it looks like this. Here we have minus comultiplication plus 0. So one factor we do not map to it. And then we just glue this from these three copies accordingly. I mean, I can write it more explicitly, but I think everyone gets the idea, right?
Ну, сейчас уже времени больше, времени мало осталось. Okay.
Yes. So here we need to
also deltas.
Yes. So we do not do on anything on one of the circles, and on the other one, just map it using that. So, is it right? Yes.
Okay, and what are the homology?
So the cohomology is yeah, that's a good question. Well, I mean, we have two-dimensional cohomology in okay, so I mean, we can deduce it from here. So we have sorry, one moment. We have one-dimensional cohomology in degree 3. We have one-dimensional cohomology in degree 2. Well, let me just write the normalized polynomial here. So we have and so we deduce that we have one-dimensional cohomology in degree 2, one-dimensional in 3, one-dimensional in 5, and basically one-dimensional in degree 9, but it's it should be shifted so as to facilitate this minus sign. I think like this, but maybe I'm incorrect.
Okay, thanks. We should stop here, I believe. Are there any questions? Any other questions? No. Then, thanks, Grisha. I hope you did not suffer too much.